Part 2 of fancy counting, I've entitled this ordering, like last time, but make it weird. So in the part 1 video, which hopefully you've watched, it's kind of the foundation for all this stuff, we talked about ordering ordering items. Just look at this. I'm going to show. So in order to take this video, we're trying to get rid of background noises. And just a couple days ago, we bought our cat a little water fountain. Look at this. It's like a little water fountain. So normally it like shoots water out from the top of that pineapple, and I will turn it on so you can see what it's like. And so it's like running water that she drinks from. See? But it obviously makes a lot of noise. And so when we tried making the video the first time, it was like making a lot of noise, so we had to turn it off. And whenever we turn it off, she like gets really curious as to why it's off, and she wants it back on, and she keeps like licking the edge of the pineapple because she doesn't understand why her water is off. That's all. Okay, okay, back at it. It's cute. Okay, here we go. Okay, so in the first video we talked about ordering and ordering different objects. Okay, we did the example of, now she's scratching on her scratch pad. Anyway, it's fine. Ordering different objects. And we talked about if we have like 5 different objects, the number of ways that we can put them in order is 5 factorial. That's where this factorial notion came up. So like 5 objects. You can't see this one super well, huh? The way to order 5 objects is 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. Let me get a new marker. But I'm going to present a new problem for you, which is what if you can't tell all of the objects apart? Okay, so come over here to see my explanation here. New scenario, so your mom has packed you 4 snacks in your lunchbox, but different than last time, so we used to have a yogurt, a granola bar, a cheese stick, and a fruit, but now instead of a fruit we have 2 cheese sticks, which we can't really tell apart. But we're trying to figure out how many orders we have to eat this, okay? So, for instance, one order would be we eat the yogurt first, and then we eat both cheese sticks, and then we eat the granola bar, right? In the last video, we talked about how we have like 4 options, and then 3 options, and 2, and then 1. So, like, if we could tell all of these apart, that would give us 4 factorial options, which is 24 options. But that idea of 4 factorial counts this as one option, and it also counts this, right? And to us, that doesn't mean it. Like, it doesn't matter whether it's this or this, right? That's the same setup for us because we can't tell these 2 cheese sticks apart, right? So our 4 factorial is overcounting because it doesn't realize that we don't know the difference between this setup and this setup, right? Like yogurt, cheese, granola bar is the same as yogurt, cheese, granola bar. So pretty much in every setup, like even if we had split it up, like if we had cheese, yogurt, cheese, granola bar, our 4 factorial is still counting this as one and this as another. So for every setup, it like double counts kind of. So we have to figure out a way to like counteract the fact that it is double counting. And in every setup, it double counts by however many ways there are to order the things that we can't tell apart. So in this case, we have 2 cheese sticks that are identical. So there are 2 factorial, which is just 2, ways to rearrange the cheese sticks whenever we have it set up. So the way we're going to counteract this is by dividing it out. So follow me back over here to the board. Okay, so in our previous example, when we did 5 objects, 5 factorial, maybe I should add that this is like distinguishable objects. As in, they're all different. In this scenario, we have 4 objects, but 2 of them are the same. 2 the same. So the way we can count the number of arrangements is we do our 4 factorial, which is the number of ways to order all of them. but then we have to counteract the fact that two of them are the same. So we'll divide out by 2 factorial, which is the number of ways to order the indistinguishable cheese sticks, which is indistinguishable cheese sticks, which is coincidentally the name of my next album, Indistinguishable Cheese Sticks. Okay, 4 factorial over 2 factorial, so that is 4 times 3 times 2 times 1 over 2 times 1. Here's a 1, here's a 1, so really we just have 4 times 3 times 1 times 1, 4 times 3, which is 12. Which makes sense, remember, our 4 factorial is 24, and when we were, like, showing our examples, we decided that it double counted every option, so it makes sense that we actually only have 12. So let me give another example of this. And this is a question that I've seen before, like on the ACT or something like that, so you might have seen one like this, that says like, count the number of ways to rearrange the letters in the word bananas. Okay, so we have bananas, and we're trying to figure out how many different ways there are to rearrange it. So, like for instance, one rearrangement would be B, N, N, S, A. So that's what we're talking about a rearrangement. We're just mixing up all the letters, right? Let me get rid of that. So the way we can count the total number of arrangements is we say, well, we have 1, 2, 3, 4, 5, 6, 7 letters. So if all the letters were different, there would be 7 factorial ways to rearrange the letters, right? But we have these repeated letters that we can't tell the difference between. So we have 3 A's. Okay, so we're going to have to divide by 3 factorial because of the A's. And then we have 2 N's repeated. So we're going to have to divide by 2 factorial because of the N's. There's only one of the B's, so we can't get that confused. There's only one of the S. So this is what we're going to, this is our final answer. 7 factorial divided by 3 factorial times 2 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. So let's see if we can find some fancy ones in here to reduce this. 1 over 1 is a fancy one, 2 over 2 is a fancy one, and then there are a couple different things you could do, like I see this 3 times 2 and that's 6. That makes a fancy one. So all that's left then is we still have our 7 on top, we still have 5, 4, and 3, and just dividing by 1, so we don't need to write that. 7 times 5 times 4 times 3 is something. 35 times 12, which is, let's see, 35 times 10 is 350, plus 35 times 2 is 70, so I think our final answer is, oh, 420, I forgot, 420, blaze it. I knew that was the answer, because it ends up being 420. Hilarious. So there are 420 different arrangements of the letters in the word bananas.